today we are going to continue on the Rakov model. Okay, and for those who have not attended last class, so Rakov is a model that was proposed in 2023, got published in Findings EMNLP. That was a model to bridge certain ideas that you find in RNNs, which is the recurrent modeling idea of language model, and the self-attention idea or principle of transformers, right? So it's kind of like bringing in the best parts of both the worlds, and then an attempt to figure out whether we can do a linear time contextual embedding generation instead of the standard classical quadratic time contextual embedding generation that happens in self attention based transformers, right? Okay. So you will get the lecture, so don't worry about it. So yeah, so we are in a phase where we are looking at some of the the performance of Rakov, right, and how it performs with respect to other transformer based models, right? So we saw that this the standard ARC challenge, and it does pretty well in terms of how the accuracy increases as you increase the compute. And by compute, what we mean is the model size and the data set size multiplied by the training steps, right? And we see that as you give it more compute, it starts performing much better than the other transformer based models like Bloom and Pythia and OPT on multiple choice science questions, right? HeLASWOG, again, that's basically a task where you pick the most plausible continuation of a short story. So you are given multiple options and the model has to choose one. Over there also you'll see that the same thing is happening. It's performing as good as the other models. The Lambda OpenAI challenge, which is predicting the final word of a passage given full preceding context, that's sort of like tries to check whether to what extent the model can is sensitive to long range dependency, right? And over there also the model does pretty good in comparison, almost nearly as good as the other similar sized transformer based models. This is the open book QA task, and where small science reasoning tasks are given, and you just have to extract the facts from an open book sort of a setup. So you are given an open book in terms of basic science corpora or data, and you need to answer certain factual science questions, kind of like a quiz questions. And over there also you can see that it does pretty well as compared to others as you give it more compute. Record is a test where we try to understand the reading comprehension along with the common sense reasoning. And again, it's a closed style question answering, which means fill in the blanks, So basically you mask certain entities in the passage and you ask the model to fill those entities in the passage, right? So and over there also you'll see that Rakov sort of not as good as the other models, but starts getting pretty close when you increase the compute, right? and we'll look at we'll discuss this particular aspect, like what happens when to Rakov when longer longer contexts are given to the model, and why it starts failing on longer contexts as compared to shorter contexts, right? So this is a very standard long test for longer context sensitivity. So this is a long range arena test. So essentially there are multiple tasks within this test. So it's a collection of synthetic and real data sets of text, image, math, and it's with longer, very long sequences, up to like 16,000 tokens, which is quite long. And there are different types of tasks, like list ops, which is solving nested math expressions. It's quite a challenging and open task even today, till today. Text task is basically read a long article and decide if it's about a certain topic. Retrieval example would be like whether find, as an example, find where Mary first appears in a 2000 word passage. So that would be a retrieval sort of a task. Image, they just flatten out a particular image data into a sequence of pixel, quote unquote, words or tokens, and then they try to do some sort of classification or something like that by reading over that entire sequence, row by row, right? Pathfinder is like kind of like puzzle sort of challenges, where you have to see whether two dots in a maze are connected via a winding path and that sort of problems. PathX is a extension or more complex variation of Pathfinder, and it's basically you test the same thing. So you ask the model whether the two dots are connected, through a very complicated winding path. So okay. So in the long range arena test, we see that Rakov actually does pretty comparable on, let's say, list ops and text and retrieval and so on. Even on image, the last row, you have to look at the last row as compared to a lot of these other very latest transformer based models which are able to capture long ranges. However, when it comes to challenges like Pathfinder and PathX, it wasn't. I mean, PathX wasn't really something that was sort of done. But if you look at Pathfinder, Rakov did not do that good because the context is pretty long, and that's one reason why it didn't do that well. We will look at S4. S4 is one of the state space machine models. We'll look at S4 in the next class. But interestingly, S4 does really good on the LRA challenge as compared to all these other state-of-the-art transformer-based models. Now, if you have to look at Rakov versus LLMs, so how do they perform? So what the task was, 4 different tasks. Like the first task was an entailment task, RT, which is basically trying to figure out whether the model can do certain logical inference between two statements, where one statement would be the premise, as an example, John loves Mary, and the other statement would be a hypothesis, which is, let's say, John cares about Mary, and it needs to say whether it is true or false, which means whether the second statement, the hypothesis, can be formed out of the premise, right? So that was one kind of test. Then there was the natural language inferencing test, the wiki-based natural language inferencing test, and it basically tests certain co-reference resolution challenge, understanding whether the pronoun reference is correct or not. So as an example, if there was a sentence like the trophy doesn't fit into the suitcase, and then there is a follow-up sentence which has because it is too small, a follow-up clause or a sentence, then it should be able to detect that it actually refers to suitcase. So whether that happens or not. So that's the second task. The third task was the go emotions task, which is basically emotion classification. And the fourth was PAL-EMO 2, which is aspect-based sentiment analysis, which means a sentence where there are multiple aspects, not just one singular aspect, which is let's say the negative or positive sort of an aspect. So it tries to check to what extent the model can actually detect multiple aspects that are present within a particular sentence. Like the food was delicious, but the service was slow. So it has two different aspects, a positive aspect and a negative aspect, right? And what happened was, so these are the tasks on which Rakov was challenged with respect to the LLMs. So what they did was they first created something like the Rakov GPT sort of a family, which is basically Rakov at the base, as the base model, and they try to do some zero-shot, instruction like inputs, and try to see whether there is in-context learning capability within the Rakov model, right? So they took Rakov 4, Raven 14 billion model, and evaluated that under this ChatGPT style prompting techniques. And they also created another version, which is the same thing, but what they did was they fine-tuned it through certain instruction, basically what we call as instruction tuning. So they did some instruction tuning on Rakov and came up with this version which they called Rakov adapted on certain conversational and reasoning data, right? So just for certain, to check whether it aligns better in terms of following instructions which are ChatGPT style prompt-based instructions. And as you can see that for each of these four tasks, they sort of compared with ChatGPT GPT-4 as the state-of-the-art LLMs. And they also showed at the final, in the last column, you also see what's the best as of now, as of then, which is 2023, what was the best result. And you can clearly see that the moment you do instruction tuning, Rakov, the performance immediately jumps up for RTE, even to some extent for NLI, and to some extent for PAL-EMO 2, right? However, for certain reasons, the Go emotions didn't really jump up that much, and it wasn't that good, which means emotion classification is not really good for when it comes to Rakov, right, as compared to ChatGPT. But if you look at Rakov adapted, it pretty much starts coming closer to at least ChatGPT, if not GPT-4, right, for RTE and at least for RTE. So clearly it's not like the Rakov 4 as of now. I mean, right now there is the current Rakov version is Rakov 7. They did a lot of other interesting things on top of that, but the original Rakov 4 clearly, even after instruction tuning and all, is not really a model that you can just replace that, replace ChatGPT or LLMs with that sort of a model, and can use that for certain more complex tasks. So is there a fundamental limitation, right, for Rakov? So if you look at the most key, the core of the Rakov model, you see this recurrence of the state AT, where alpha is the exponential decay that you apply on the previous state, and beta t is the update gate that is applied on the value, right? And then you do you get the final state st as some sort of a percentage of the value, right? And that comes out of dividing at by bt. So basically every pass token of this sentence, let's say John loves Mary who lives in New York City, gets compressed into this single vector st, right? So that's what is going on, and at every time step all the pass tokens are getting compressed into that particular state. If you unfold it, you will see we saw that. So in our running example, as an example, so John would be, the decay would be alpha raised 5, loves will be alpha raised 4, Mary will be alpha raised 3, who would be alpha raised 2, lives will be alpha raised 1, and in would be alpha raised 0. Where are we at? We are at the step in. So we are at the in step. So at the time step where you find the token, where the token comes, where the new token is in, this is what is going on in Rakov, right? So the entire prior sequence is compressed at that particular time step state, but compressed in this fashion, in an exponential decay fashion. So basically John is nearly forgotten, as you can see, right? And if because of, and also because of the factor that, let's say for an example, just as an example, let's say that beta is small, then it will be basically nearly forgotten, because you're not beta is that knob which helps you to retain the essence of John. And if beta is also small, then it will be forgotten. So alpha is the knob that basically does the decay, and beta is the knob that refreshes that information back. So if the refreshing is not happening, if that is small, then it's going to faint, right? So that's what's, let's say in this example, John and love's happening at the stage when you get to in, right? Mary may be still active just because of the factor that the weight beta for Mary is medium, who may be moderate, so it's just basically a syntactic link, is the glue, causal glue. Lives is high, so it's very fresh, and in definitely will be strong because that's the current token, right? So this is how things move. It's just a example of how things move in Rakov. Now that's the information bottleneck, because you cannot, it's very hard to bring the influence or the or the effect of past words if they actually matter, because most of the times they will be forgotten, like John got forgotten. So that's the information bottleneck that is intrinsically there in Rakov. Okay, so just as an example, if you look at the Vinogradhi task, which is basically pronoun resolution task, which actually requires a good amount of long context understanding, you'll see that Rakov is not doing really that good as compared to other models. And we also saw some examples before as well, if you remember. And this is the reason that of that decay, of that exponential decay, that although it can take a lot bigger sequence, but it starts forgetting them also because of that, because of the alpha. Okay, so what else might be going wrong? So Rakov updates memory in discrete time steps. So every single time step a new word comes in and it updates the state and in this fashion, right? So it's elegant, it's efficient. You can parallelize the updates and make it linear time. However, as we saw that it kind of starts forgetting the past. And but the problem is that language meaning flows like almost like a fluid between tokens, and doesn't really the semantic drift doesn't really happen as a jump at every token boundary. If if, like, as an example, let's say John loves Mary who lives in New York. Now Mary was the object of John and loves, right? So Mary was the object of loves subject was John, and then in the second part of the sentence, who lives in New York, Mary becomes the subject of live. Now this transition from object to subject has to be smooth. Smooth in what sense? Smooth in the sense that the content of the embedding cannot just move from one coordinate and jump to a very different coordinate of the embedding space. If you have to look at the embedding of the state as of now until Mary. So the moment Mary becomes the subject from the object, what happens in Rockover is there's a sudden jump of the state from the previous state to there's a sudden jump of the previous state to the next state, just simply because Mary has become a subject. And it starts believing as if, like, okay, the conversation has all moved into a very different theme or topic. But it's not really so. If you look at Mary who lives in New York, is not disconnected from John John loves Mary. So it's not that the topic has suddenly moved to a very different thing. So there has to be, so the topic is still within that neighborhood of John loves Mary. And there has to be a smoother transition. So that's the problem with models like Raku. Even that's the problem with models like LSTM, right, or RNN based models. So language structure does not abruptly change. So that's the idea. So Mary must smoothly shift from the object of loves to the subject of lives. So memory should evolve continuously, not just be replaced at token boundaries, right? So a closer loop would be like, let's say you have the first word comes, which is John. That's fine. You add John, you start the subject trace, then loves comes in. You slightly forget John, focus on the verb. That's still okay, still fine. Then Mary comes in. You keep both John and love. That ideally what it should be. Ideally what that should be. That so John should not get decayed a lot when Mary comes in. But when who comes in, okay, you are adding who, but you also need to recall Mary as not only as the subject of who, but you need to recall Mary as the object of John as well. That should not be forgotten. So you cannot see Mary independent of John, right? So, but if John starts getting decayed and love starts getting decayed when who arrives, that's problem, right? So that's what we call as smoothly shifting the role of Mary, right? And then all these other tokens come in, lives in New York. Even then, John cannot be just suddenly be forgotten all of a sudden. So there has to be a smooth transition of the conversation, just like how we are discussing, right from the beginning of this lecture. Whatever I am discussing till now, there is a smooth transition of what I have discussed and whatever you heard, right? You did not completely forgotten, you did not forget what I started out with, because there is a continuation in terms of the topic. But it's perfectly fine if you forgot let's say what I taught 3 lectures back right now. I mean, that is not relevant to at this time point. But what is relevant is what I discussed yesterday, or sorry, Saturday, and what I am discussing today. And it has to be a smooth continuation. Whatever I do in the future right now, today, whatever I'm going to do in the future, there has to be a smooth transition, right? Okay. So this is the thing. So older info starts getting decayed, and that's the problem of Rakov and the similar sort of models, right? Okay. So an analogy, I like this analogy. And an analogy is like Rakov is almost like flipping through a photo album, like where every page being one word. And however, what we need is like a movie, like language is more like a movie where when the frames keep going on, you don't feel like there are discrete frames, right? You feel like it's a continuous. So even within one scene of a movie, there are multiple frames in that scene, but you don't feel that there are multiple frames in that scene, right? You feel like this is one single scene which is moving on, right? One single event that is happening within that scene. So that's how languages are, just to give you an analogy, versus what Rakov does. Okay, so the world is not just transformers. That's the lesson we got. So Rakov offers a linear time alternative. However, it is, as I said, it's bridging the world of recurrence with attention. So that was the entire idea. However, and it sets some sort of a stepping stone towards state space machines, including S4, Mamba, and all the other variations of Mamba and all of these sort of hyena and so on. So that's why I felt that you should understand Rakov, you should understand the limitations of Rakov, and then only you can go to the next state of, the next real deal, which is state space machines, which we are going to discuss today, right? So it opens up that direction of looking at state space machines. It also shows how you can bring in exponential recency within the context of attention, skip-gram attention, right? We can move on to the next topic, which is state space machines. So we are trying to continue with whatever we learned, the drawbacks of Rakov, and we are not going to see state-space machines. I'm going to, initially my intention was to cover also S4 and Mamba, but I thought that let's just slow down a bit, because this is a very new kind of concept, new kind of model, and particularly takes a little bit of time to understand the connection of state space machines, because it came from control theory people, right? So from that discipline. So how does it apply to language particularly? So that takes a bit of time to understand. Okay, so the core idea is that language is like a diffusive field. So it's almost like, let's say if the room is filled with some fluid, and you have to swim through this fluid, and the density is different at different point of this room, right? So this room is all filled with the fluid, and you have to somehow float through, and the density and the viscosity and everything is different. And how you are going to drift in this fluid, in this room, through this fluid. So imagine that language, or whatever we talk, whatever we discuss, the theme that carries over as we are having, let's say, a conversation is like that, like the fluid that keeps on changing, that keeps moving, but in a slow way. So it's a continuously evolving field, but it doesn't do some abrupt changes, right? So that's what the core idea is. So instead of discrete jumps, which you see in Rakov and like LSTM or RNN based models, state space models treat hidden meaning as a continuously evolving field where X is the state. So whatever we saw S over there, that is represented as X, and U is the current input. So U is the current input at time point T. X is the state so far at time point T. So Xt is basically the latent semantic field at till that point. Axt is how the field drifts or decays on its own. So if which means that, let's imagine that there is no other word coming up. You took a pause. Let's say I'm talking and I'm taking a pause, and now whatever I said, you are processing that in your brain. Now how that process is going to move in terms of what would be that interpretation. So if I keep on talking, then there's a smooth transition. If I talk very fastly, very quickly, then if I talk, then you would not be able to understand me that well, right? If I talk very fast. If I just give a pause, you might start forgetting what I saw, what I told so far. You might start forgetting that if I give a long pause, or you might start thinking that, okay, this is it. There is no further conversation, and you might want to freeze that thing, that whatever we have discussed so far in your memory. So three things can happen, right? One is you completely forget what I just said because I'm pausing. One is that you are anticipating, okay, new information may come in, and you are developing on whatever you have heard so far, and you are developing over that to gauge what is the real meaning of whatever you have heard so far. Or you will just figure out that, okay, this is it, the lecture has ended or the discussion has ended, and this is what I have with me, and you freeze that, right? BUT, which is U is being the current, whatever I say next, is going to nudge that memory field that is inside your brain. So every single new word that I say is going to push your understanding that you have in your brain with certain degree. So it's basically perturbs your understanding a bit more. Like as an example, how many number of times it happens to you that somebody gives a lecture and you understood something, and then he or she says something else, and you have to go back and unlearn what you understood, and oh no, I got it wrong, this is what it should have been, right? So you keep on updating what you already learned, which means you have to retain what you have and keep on updating or perturbing that understanding. So as the lecture moves on, you are constantly carrying forward what you got, and you are perturbing that information in every particular state at every particular time step, right? Okay, it's kind of like a bit philosophical right now, but you first need to understand this at a philosophical level before we get into the math, right? So this is important. So example would be John. Let's say John comes at the first word, right? So introduces a subject wave. So let's look at it like a wave, right? And loves injects a relation pulse into that already existing wave and reshapes the wave. And Mary comes in, adds a strong entity trace, and propagates forward into that wave, into the same wave. And then you have, and before who comes, that wave sort of like morphs smoothly and moves towards where whose wave or wave embedding would be. So think of it like, okay, if I pause after Mary, so let's say John loves Mary, and I pause. Now where would that wave go? So it's think of it more like that. So it starts drifting, keeps drifting, and if nothing comes, let's say, then it will decay. So it's like a sound echo. So it echoes, and the echo keeps going on. But if nobody else is saying anything in this room, let's say, then the echo will die down after some time. So it's like that, right? So think of it like that. Yeah, it's kind of hard to bring SSM. It's easy for signal processing and for speech, how to connect SSM to speech and signal processing. It's a bit hard how to connect it with language, but bear with me. I'll try my best to give you that connection. So the takeaway is SSMs view language as a fluid process, pretty much like speech or signal, and meaning doesn't jump from token to token. It flows continuously, evolving and fading like ripples in a pond. So think of it like that sort of an analogy. Okay. All right. So meaning doesn't jump is what is the takeaway, where we actually move away from RNN style models or Rakov and so on and so forth. Okay. And it's also very different. This take on language as a fluid process is very different than transformers as well. Like transformers doesn't look at it like this. It looks at it at a very discrete level, and what kind of attention is coming into a particular token from the neighboring tokens at a discrete level, right? So independently of each other. So there is no notion of how the wave carries over and hits a new word. So that notion is not there in transformers. Okay. So how every token independently influences each other. That's like John, how John independently influences, let's say, lives, or how loves independently influences lives. That's how transformer works. So what exactly is smoothness of the meaning? So if you look at this particular equation, which is the SSM equation, and it looks, forget about, A being stable or not stable and what it actually means, A being a matrix, just a linear transformation. Think of it like a linear transformation. Forget about that. For now, just look at this, the second relation that you can get out of it, which is that xt plus delta, where delta is a small change on the t, implies you would have something like an exponentiation of EA delta of xt. How do we get to the exponentiation? We will look at that derivation a bit later. But if you solve this this is an ordinary differential equation, right? dx by dt equals to ax plus bu. If you solve this, you will get that. If you solve this equation, right, with the integrating factor to be e of a delta. And you have an analytical function over t because of this, which is infinitely differentiable, and it doesn't have jumps, right? It's continuous. So that is what we mean mathematically by smoothness of meaning, which means the rate changes gradually, no abrupt token boundary jumps. The rate of change is bounded by this, which means x dot t would be the time differentiation over x, right? So that is bounded by the norm of the matrix A, can be the Frobenius norm of something, or multiplied by the norm of xt plus the norm of b multiplied by the norm of ut, right? Kind of like, let's say that a sculpture is working with a clay, like a clay pottery, and how you would reshape the clay. So you don't write, as it's the same clay and you keep on reshaping it. So that's what SSM is doing. It's a continuous process of how you reshape the clay, and it's not discrete, like every time there is a new thing to be done. And it's not like, you make how you do a snowman in Christmas time. You make a snowball, you make a smaller snowball, you put it on top of the bigger snowball, and you put a carrot as a nose. No, that's not how, that's what, Rakov or RNN would be working. That's not how SSMs work. SSMs work just like how a pottery happens, as if like the snowman in the Christmas is being done out of like a pottery sculpturing. So that's what SSMs do, right? So it makes the head out of the body only. So it's like that. So there's no edges as such in terms of jumps. Okay, all right. So to give you a visual, so how the state changes over time, which means, but by time we mean the token time steps, right? So John loves Mary, who lives, in New York City, as it goes till city. So this is how discrete updates happen in Rakuf, the blue, right? Whereas if you look at what happens in SSM, SSMs including S4, Mamba, these are all different types of SSMs only. What happens is that the influence of John decays continuously. A particular aspect of John, let's say as a subject of the sentence, that decays slowly and continuously over time till you get to the point of city, right? So the effect of John, the effect of loves, they decay gradually. And by the way, I showed you a decay. It may not necessarily be a decay. It can also be that it comes up again. The effect of John again is injected back. But even then, it will be a continuous arise. So the effect of John, if it decays, it will be continuous. If it comes up, it will be again continuous, right? So that's what happens in SSMs. So yeah, so it makes clear sense for, as I said, for streaming signals like speech and video. A bit difficult to connect with language, but you can think of it more like the thought. I gave you that thought analogy, right? If I am talking, it creates certain thoughts in your brain, and you are processing that, and you are carrying forward that thought kind of in a continuous manner as I keep speaking, and you are updating that thought that in terms of your understanding. So that's what it means for language. So solving the continuous case, so if you have to solve this this equation dx by dt, the ODE is equals to ax plus b u, you will get this solution. X of t plus delta is equals to e raised exponentiation of a delta multiplied by xt plus the integration over that period of delta, the 0 to the delta period, the small delta period, over e of a tau b of u t plus delta minus the tau, which means from when you are the variable that you are integrating. Okay, so how do you get till here? So I will show you, but basically it means that the information, this equation means that the information diffuses and decays smoothly. New tokens which are coming in are going to nudge that field, keeping while the field evolves, right? So that's the thing. So I give you a scalar intuition, and I have these slides. You can see how for the matrix how to derive it. This is the scalar equation. The scalar intuition is very simple. What you do is that you multiply this equation by you multiply both the sides. You have dx by dt equals to ax plus bu, right? You can also write dx by dt as x dot. That's basically a notation for time differentiation. And then you multiply both the sides by e raised minus at, right? Where a is a scalar right now. And if you do that, you get to this point, right? So no, it's not really working. So if you do that, you get d of dt by of e of raised minus at xt, which equals to b of e raised minus at ut. And then if you integrate over t to t plus delta, then you get this, right? It's pretty simple actually, you know. You just it's the basically the fundamental theorem of calculus, right? You just get the you integrate both the sides and you get this, and then you solve for x of t plus delta, which will give you e of a raised delta e raised a delta xt plus that particular integration factor, right? So that's how you get to the solution. And it's a closed form solution. So the exponential integration factor for the matrix form would be, you know, you just have to remember that if a is not a scalar like this, unlike here, but if a is a matrix, then if you apply Taylor expansion over e raised a delta, I mean this is a Taylor expansion, right? And if you integrate over that, you will get something like this. And by the way, you know, if you differentiate over with respect to delta for e for the Taylor, this is for the Taylor expansion, just to so that you understand how the square is coming and the cube is coming. So if you just do the differentiation with respect to delta of e raised a delta, you get this, right? Okay. So you can go through these things, you know, how to solve for the SSM ODE for the matrix case, but finally you will get this final, whatever you see in that box, which is the final expression, the equation. So some special cases, so you just have to understand what really is going on in this solution. And why this solution is important is very simple. You know, you can get these special cases, get to understand these special cases, like what happens if there is no further, that pause. No input means pause, which means the thought is stuck in some sense. No new words are coming in. I'm not talking anymore. So that would just be that x of t plus delta, whatever is that drift is happening. The drift is a function of e raised a delta xt. So it's an exponential drift. Now can be a decay, can be a increase, can be an oscillation, whatever that is, depends upon what a is, but depends upon the nature of a, the matrix A, but it could be, it's basically an exponential drift of your thought if no further input comes in, right? No dynamics means a is zero. A is zero means it's basically a collapse. You know, the matrix doesn't really exist in that sense. So in that sense, it would be xt plus, it would be just xt and whatever is that term. Infinitesimally small step delta, you can see what it means. It basically comes down to the very simple case of ax plus bu, right? So that's the thing. Anyway, so how to interpret this delta for language? So between Mary and who, let's say there is a delta between Mary and who. Now Raku, for Raku, it simply waits. So it's just discrete update at next token. It just waits, it does nothing. It just stands still and waits for the next word, right? For SSM, it doesn't wait. It waits. It doesn't wait. It doesn't stand still. It starts drifting a bit more till the new word joins in, right? That is where the continuity comes from, right? So SSM treats that interval as a smooth semantic drift. The meaning of Mary gently morphs from object of loves to subject of lives. Okay, so that's the reason how you can actually, so it's almost like a affine, let's say a spline, and there is a curve till a particular point, and you are just bending that curve, continuing till the next point, and again you are bending from there till the next point, and that curve is your semantic drift. Instead of doing something like tuck 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 tuck, instead of that, so you are just keep on bending that curve like this in a continuous manner. So that's what is happening here. So delta measures this conceptual span. So it's not really a real seconds sense, which can happen for signals and speech, but it's basically a conceptual span. Okay, so delta controls how long the internal state xt evolves before the next token arrives. So the linguistic view acts as a semantic time step, how far meaning drifts between the words. So which means if the two words are very different than each other, let's say Mary and then something completely abruptly some other word comes in, then the drift will be quite far. It will drift quite far away and then it will catch up with the next word. So that's what it means, how far meaning drifts between the words. Okay, so if it's a very different topic, or if the topic ends, as an example, let's say full stop, you get a full stop, the drift will be a lot more after the full stop, because now you know that a particular topic has ended and a new topic will arise. Let's say the paragraph ends, that drift will be even more, right? But the sentence hasn't ended, just certain words have come in, the drift wouldn't be that much, right? So that's what it means. So normal flow would be like let's say that if semantic space is steady, which means just a simple language, for all practical purposes, delta, you keep delta as 1 only in language for all practical purposes, right? Because is usually that sense of this sense of slight hesitation, and and then there is something like that happens in speech, that doesn't happen really in textual language, right? In speech it happens that I'm hesitating before telling you something that might mean something. That really doesn't happen in text. So if in text John loves Mary who lives in New York City, it's a steady semantic pace, you can keep your delta as 1. Small delta greater than 1 would mean short pause. Long pause would mean that the delta is very, very much higher than 1. Rapid speech is essentially when I am not able to understand anything, the tokens are arriving very fast, which means you're speaking very fast. So that would be delta less than 1. And variable delta, which means that's irregular, which means it's very so those sort of sequences is very difficult to understand what really you are trying to say. So it's incoherent, very incoherent conversation that I am having with you. That would be oscillating, sort of an oscillating delta. Sometimes it's greater than 1, sometimes it's less than 1, and so on, right? So intuition is again the same thing. Again, what happens if the flow stops? Two cases. Case 1 is that the sentence has ended, which means there is no xt plus 1. So xt plus 1 is xt only, and the semantics just freeze. So it's almost like you're watching a movie and you're pausing the movie at certain points. So it just froze there. So there is no drift going on further, right? So there is no delta in that case. In the second case, there will be some delta and it will start drifting. So xt plus delta exists, and it is e raised a delta xt. So even if there is no new u, the drift will be there because it is anticipating that new things will come up at some point or the other. So that's why, which means unfinished sentence as an example, right? So it knows that something is going to come up. The next word will be written, or I will read the next word at some point. So in practice, language models freeze state. So case A, after every sequence ends, but the math allows case B. As I said, it's useful for continuous signals like audio. Any questions so far? I know it sounds a bit tantric, esoteric sort of a model, right? And particularly for language. Any questions? Anyone so far? Before I move into A, now we have to see what A means. I have to be quick. So A governs how internal meaning drifts when no input arrives. Now it can be a decay, it may not necessarily be a decay. So that's what we are going to see. So this is what we have seen so far. Now, if imagine that A is diagonalizable, which means you can do a eigen decomposition of the matrix A. A is a matrix, right? So in that case, what will happen is that each of the eigen vectors will represent a particular aspect of this meaning, of the semantics. And I'll give you an example. And the eigenvalue represents the intensity of that aspect, in the sense of whether that aspect will decay or will intensify, right? Or will be remaining as it is. So think of it like the A matrix contains all the different aspects of the meaning, right? And every eigenvector will represent one of those aspects. And as A moves from time point T1 to T2 to T3, certain aspects will die down, certain aspects will reinforce, and so on, right? So the eigenvector, as you know, is like this semantic direction that you get over time. As an example, let's say John loves Mary, who lives in New York City. So let's say that let us write the lambda, which is the eigenvalue, as in terms of both real and imaginary, because sometimes it can be imaginary as well. So let's imagine that it has an imaginary component to it. Then you can rewrite e raised lambda I for that particular vector, that particular eigenvector, as this, right? So if you have an imaginary component, you can rewrite it as like this. Then if you decompose, you see there is a real part, which is AI, which tells you the exponential growth or decay of that aspect, of that amplitude, means of that aspect. And the imaginary part, which is BI, tells you the oscillation, because it's a sinusoidal curve, right? It's a sine curve, so it tells you the oscillation of that particular aspect, whether it will recur, whether that aspect recurs over time, comes back over time or not. That will be that you can check from the imaginary part. So as an example, the linguistic intuition is that if AI is less than 0, which means that memory decays exponentially, right? Like Mary eventually fades. AI equals to 0 means memory persists. John stays in focus across the sentence, right? And BI, if BI is not 0, which means there is a, lambda is a complex number, it's not, which means BI is not 0. It means that that particular aspect will recur, will reappear. That's what it means, right? And together, if you sum all of this up, then it's almost like every eigenvector is kind of talking in sort of like in almost like an orchestra. I like to look at it like that. Like every one of you is an eigenvector, and every one of you is in a flux. Sometimes you intensify, sometimes you stay the same, sometimes you decay, and together all of this, whatever is going on in the room, that is A, the capital A, right? So for as an example, Q1, which is one of the eigenvectors, let's imagine, can be the entity mode. Let's say it tracks proper nouns like Mary or city. So that is one aspect, proper nouns, right? And if there is a small negative real part, it means slow decay. So the proper nouns will always be kept intact. That is what it means. Q2, let's say predicate mode, which is the predicate aspect. So loves, lives, and so on. So medium decay. And Q3, let's say the syntactic rhythm, like who and all these clausal clues and so on. So it may have, because you can have this coming back, who, which, while, it can keep going on, and you can stretch that sentence like this, right? So it can come back over time. So it has an oscillatory behavior, right? And Q4 is the function words like in, the, and so on, that glues everything into a phrase, right? So it can fade fast. So if you collect all of these eigenvectors together, sum it up, you get the overall xt. So that is how you should be interpreting a SSM. So what does it mean for A to be diagonalizable? We just discussed. So non-diagonalizable A. Now the question can be, why A needs to be diagonalizable? A may be something that is non-diagonalizable as well, right? But then the problem with non-diagonalizable A is that it becomes much harder. You won't get those eigenvectors. It becomes much harder to interpret it. What is really going on as A evolves? It becomes much harder to interpret and to control the learning, right? So how to ensure diagonalizability? So that is the reason why when you are initializing A, the matrix A, before training, when you initialize A, you cannot just do a random initialization. This is the reason. Because if you do the random initialization, you won't get all these good things, these three good things. Like, so easy to exponentiate, which is from the computational point of view, you get this independent eigenvectors, which is easy to understand what's going on, and so on, and that's why there are all different ways of initializing it, which I put in that table, right? So like you can have all the distinct eigenvalues computed and construct the matrix in that manner, the A matrix in that manner. You can do a Hermitian symmetry. You can make the A matrix, initialize the A matrix such a way that A is symmetric or A is Hermitian, for that matter. If you want to make Hermitian, means if you want to have the complex parts as well. Normal matrices also you can do that as well. You can do you can keep it in a spectrum form as well, just like what I just showed you. You can do it that way also. And there are many other things, like many other ways of doing things, such that you can guarantee certain you can guarantee these full rank eigenspaces. So basically the idea is, can we seed it in a way such that we can guarantee full rank eigenspaces, right? So that's the idea. So the key thing is that we need to design it, which means when we randomize it, we don't randomize it, we actually seed it in a very thoughtful process manner, right? Like if you look at Mamba also did the same thing. If you look at S4 did the same thing. S4 does just computes the lambdas and creates the diagonal matrix, and that becomes the A for S4, right? Rakov, interestingly, is a very trivial form of A. It's that minus W, which you saw, multiplied by an identity matrix, which makes it minus W only. So there is no drift or nothing, because it's identity matrix, right? So it just stays where it is. So if I have to look at Rakov as a special case of SSM, it just doesn't make sense, but from a math point of view I can do it. I can show that okay, Rakov also has a exponentiation of a, which is that alpha. That alpha is basically e of capital A, where a is minus w and multiplied by the identity matrix. As simple as that. The alpha that was there to control the decay, right? So interpretation is that diagonalizability ensures a acts like a set of independent semantic resonators. So coming up for next class would be S4 and Mamba, which are particular realizations of SSMs only, right? So we'll look at S4 first and then Mamba as two different types of SSMs, right? Okay, any question? Any question regarding, see, there are two things that if you understand them well, you have understood SSMs. One is the delta and one is the A. So it's not just any linear transformation that you just threw into the equation and let that learn. That's not how SSMs work. There's a very, very clear meaning of A, because if you don't do it that way, you will lose the continuity. So the eigenvalues, the eigenvectors must mean something for the semantic drift to be meaningful. Yeah, like what happened here, like these guys actually do that. S4 does it. A is basically the diagonal matrix where you keep all the eigenvalues. Yeah, or you can do it even like this also. Well, S4 doesn't do that, Mamba doesn't do it, but you can do this also. I mean, you can do look at the third row of the table. You can do the no, not the third, the fourth row, explicit spectral form, like the decomposition, the eigenvalue decomposition that we just did. You can just do that and keep A, compute it backwards like that. Okay, so I will create an A such that A is diagonalizable and A is decomposable in terms of eigenvectors. So I create a Q, I look at the lambda and then I just decompose and create the A. I can do the other, I mean, I can go backwards and I can create A and I can initialize it that way as well. There are many interesting, like there's something called hippo, like what S4 does. So there are different ways which I'm not aware of, but there are a lot of research that happens for SSMs, people who work in SSMs. There are a lot of research that goes on in how to initialize, because that is extremely important when it comes to SSMs. When it comes to transformers, no, you can just do a random initialization out of some Gaussian distribution or something, and then you can let the training do the job. For SSMs, you are at a risk. You can do it, but people don't do it, right? So now probably you are in a better position to understand why I started out with Rakov. That the essence of recurrence together with attention was needed to help you, transition into SSMs. That's what I thought. And SSMs, as you can see, they are very, very competitive in terms of performances. Very, very competitive. Like the long arena performance table that we saw, where S4 performs so well as compared to the other models. So they are very, in fact, they are pretty competitive even in terms of the most latest LLMs as well in many of the standard benchmarks. Okay, then fine.